Good morning, everybody. Perfect timing in terms of the order of the talks. Vipin's was a great setup for ours. And I'm going to do a little bit of a deep dive into remote sensing and take a bit more of a commercial lens than what Vipin gave. So that being said, let's talk a little bit first about who we are at Telus Labs. We are a company combining decades of satellite imagery, that is the remote sensing data that Vipin talked about, with a machine learning platform to answer critical, time-sensitive economic and environmental questions. So we are the brainchild of David Potier, who was with me at the Boston Consulting Group, and Mark Friedel, who is a professor in geography and environment at Boston University. And they've known each other for years. I've known them. And over lunch one day, they were talking about, there's an opportunity here to commercialize what you do, Mark, and let's go with it. So we did. And the premise of the company is that data derived from these remote sensors are going to be invaluable for answering globally meaningful questions going into the future. And that these data are inherently really difficult for the average data scientist to use. As Vipin pointed out, and I'm going to go into a little greater depth on, but our goal is to help democratize these data and start the process of using them for answering meaningful questions, both from a sort of a humanitarian perspective, but also from a commercial perspective. So backtracking just a little bit, you got an overview from Vipin on what remote sensing is. I'm going to go into a little bit more depth. So it is a measurement of Earth's land, water, and atmospheric properties using reflected or emitted electromagnetic radiation. So that's a fancy way of saying that we're basically taking pictures, right? But this is not, pictures with your iPhone. The sensors that we're taking pictures with are capable of capturing radiation that's reflected or emitted from across the electromagnetic spectrum. So that visible band there, you probably recognize this, this graphic from physics classes back in high school or college. That visible band is what your iPhone is taking pictures of. But what these sensors are taking pictures of is across the magnetic spectrum. And so it depends on what sort of phenomenon you're looking at, which part of the spectrum you want to look at. But we'll talk about that a little bit more later. But the sensors that we're talking about here are typically satellite-mounted sensors. There's been a lot of work recently in terms of mounting these on unmanned aerial vehicles. And there's a wide variety in terms of the types of satellites, which we'll talk about in a little bit. And yeah, Vipin had a much cooler animation. I just have a picture of the satellite taking the pictures. But okay, so now for a history lesson. Does anybody recognize this image? Crickets. Okay. So this is actually the first image of the planet Earth that was taken from space. So the story behind this image is in 1946, there was a bunch of scientists, I believe it was at Los Alamos. They were launching German V-2 rockets that they had taken from the Germans after World War II, and they had the bright idea of putting a camera on one of these rockets. And so they launched this. It went up. It took some pictures. It crashed, and out of the wreckage, they pulled the camera, and miraculously, it survived. And they were ecstatic when they realized that there were pictures of the Earth. So they knew that they were onto something with this. So fast forward 26 years later, and we have this beautiful image, which you've probably all seen before, referred to as the blue marble photo. It was taken as part of Apollo 17. And this was the first time that we had captured the entirety of the fully illuminated Earth, almost fully illuminated Earth, in a single photograph. So that's only 26 years later. So there was some massive advancement there. Also, in 1972, we launched the Landsat program. This is humanity's longest-running satellite imagery collection program, And it continues today, as we heard from Vipin, scientists are still using this. This, along with Modus and a couple other sensors, are really the bread and butter of a lot of the remote sensing science that happens now. And so Landsat has captured millions of images of the Earth's surface over the years. But we didn't stop with Landsat, though. So as of 2016, there were thousands of satellites in orbit around Earth. And of those, about 400 are dedicated to the task of Earth observation. So either taking pictures or other measurements of the condition of the surface of the Earth. So many of these, as we saw before, offer their data to the public domain either free of charge or via a fee. And yeah, so this shows only a small sampling of the sensors that are out there. And in the numbers that I gave before, I'm not even taking into account the advancements in CubeSats, these little micro satellites that private companies are launching nowadays, and they're collecting even more information. So bottom line is there's a lot of data, a lot of remote sensing data out there. And how much are we talking? So as of 2016, I checked recently, the NASA's Earth observation data system held 18 petabytes of data, and it grows at a rate of 12 terabytes a day. And this is just their imagery data, and it's just NASA. So you can imagine, take that, multiply it by a couple other countries and private companies, and we're talking about a lot of data. But the problem is that until recently, these data were basically stranded. They're locked up in government data centers. They're essentially created by scientists for scientists. And so cloud compute has taken some of the friction out of acquiring these data. Amazon and Google both have the Landsat archives and Modus data freely available for the public to go and get from their S3 and Google Cloud, respectively. But the know-how to navigate these imagery and convert them into clean, analytics-ready products is scarce. And for the last mile, machine learning, the development of machine learning over the past couple of years, combined with the cloud compute, has really helped build up to like a moment in time right now where we have these massive data sets of remote sensing imagery that have been collected over the past 30 some odd, 40 some odd years. And for the first time in history, we have the compute that we can actually do something with them. And now we also have the tools to look at this in not such a bespoke manner. We can do more automated processing. So the result historically has been that important questions go unasked because there's a specific role for the scientists that are working with these data. They get funded on specific grants for specific questions, but there's more questions out there that can be answered. And so there's a commercial opportunity here, and TellusLabs has seen that, and we're working to help democratize these data and make them more accessible for decision makers. And so we'll talk about how in a bit, but I want to do a deep dive into some of the challenges of working with these data. And again, you saw a bit of it with Vipin's talk, but this is part of the reason why these data aren't used much outside of the scientific community. So a couple points here. Data are locked up in unfamiliar and non-user-friendly formats. They're built by scientists for scientists. Have you ever tried to open a GRIB file? Does anybody know what a GRIB file is? Yeah, it's not fun. And there's not great documentation. I mean, it's getting better, but like it's not a database. It's not a columnar tabular data that we're used to working with. So they're unfamiliar to traditional data scientists. Data volumes are exceptionally high compared to traditional data. And when working with imagery data at scale, there's really no playbook or off-the-shelf software that are available to do this type of work. I mean, there's been work recently with Google Earth Engine that has been wonderful, but it's not a commercial platform yet. So with Google Earth Engine, you can answer questions like, across the entire globe, find me areas where we think there's water. So flooding, for example, to Vipin's talk. You can ask questions like that, and you can get answers very quickly. But if you're using it for commercial purposes, it's not really allowed. And then the images are always a mess. You saw some examples in Vipin's talk about just the missing data. And it's not just missing data too. I mean, just think about the complexity of taking pictures of a round object, and these sensors are flying at 28,000 miles an hour, and so there's blur at the edge, and the pixel size you think is consistent across the image, but it's really not. And so you have to correct for all of this, and it's quite a challenge. And then the other thing is that there's trade-offs in working with data from different sensors, which I'll talk a little bit more about in a few slides. But first, just to drive the point home about the data being a mess. So here's some Modus imagery, and this is not raw imagery. This has already been pre-processed to a certain extent. So it's been mosaicked together, and there's probably been some correction that's happened. But this is near raw, and you can see what information are we going to get out of that? If you can make it out, it's of a picture of North America, but there's massive weather systems covering up most of the country. So thankfully, people at various labs across the country and researchers put out some great products that take those raw imagery and turn them into something that's usable, like what we see in the image here. And so I'm not going to go into the gory details about how that happens, but suffice to say, it's not easy, but it's critical for the type of work that we're doing. And what we see on the screen is a type of data that can help us drive decisions. And then the last thing that I wanted to touch on, because it's pretty important, is a double click into the trade-offs in working with data from different sensors. So when you're working with these data, and if you're designing a satellite or you're deciding what data to work with, you've got some pretty important decisions to make, and there's trade-offs around the data. And so there's a couple different dimensions that trade off against each other. So spatial resolution. So that basically that means what is the pixel size? So how granular is the photograph? So you remember back I don't know, 10 years ago, if you had a digital camera, how grainy the pictures were if you zoomed in. Now it's completely different. The resolution of the photographs has increased dramatically. So this is an example of the spatial resolution. So the sensor taking a picture of the surface of the Earth. How crisp is that picture going to be? The temporal resolution refers to how often the satellite can capture a picture of a given location on the surface of the Earth. And remember, I mean, the Earth is really, really big. And even though these satellites, like I said, are flying at 28,000 miles an hour, it still takes a while for them to cover the entire Earth. So as Vipin said, with Modus, you get 2 pictures a day. But with Landsat, you're only getting 1 picture every 16 days. So there's a trade-off there. And the spectral resolution too. So how much of the electromagnetic spectrum can you cover? And that depends entirely on your sensor. The temporal extent of the data. How far back does the record go? Some of the new sensors that are being put up have, they've solved some of the trade-offs in spatial resolution and temporal resolution by chaining these satellites together and things like that. But the temporal extent isn't very long. And then the maturity of the instrument. And this is important because the longer the instrument has been up in the air, the longer people have been able to understand how the instrument works. and they've done more work to calibrate it and account for things like atmospheric effects and sensor decay. So I mentioned that these are all trade-offs, right? So for example, the spatial resolution of an image, the higher the spatial resolution you can get, you trade that off against the frequency of the imagery, and often the spectral, the depth of detail in terms of the spectrum. So yeah, I gave the example of Modus and Landsat. And then another one is the recency of the technology and sensor versus the longitudinal quality of the archive. Again, something like Landsat that has been in operation for a long time and has had numerous missions and numerous scientists working with the data versus something very new, like something from Sentinel. There's just a difference in terms of the amount of work that's been done there and the understanding of the sensor. And actually, just to touch on the point here about the spatial resolution. So the pictures on the right here give you an indication of the size of the pixels across a couple different sensors. So 1 meter imagery is something like you would get off a commercial satellite. And this is great, but you can only capture a very small extent on the surface of the Earth with that level of clarity. And then you can go a couple clicks up to 10 meter, which we're getting out of Sentinel, and the 30 meter, which comes out of Landsat, and then 250, which comes out of Modus. And so, it's like I said, it's a trade-off. What is more important to you? Is it important to get that crisp picture, or is it more important to get the temporal coverage? And so just to drive this point home, let's look at some Modus data here. So this is Modus data. As I said, it's a twice-a-day repeat. We can see there's a lot of noise there in terms of the weather patterns. But over the course of 8 days or so, you can get pretty much cloud-free images. Contrast that with Landsat, where you get a picture once only every 16 days. And so that it's daily versus a 2-week period. And so the point of all these trade-offs, I think, is the lay person, the lay scientist or data scientist coming to these data from not having a background in remote sensing and understanding how these sensors work, is going to have a hard time matching up the right data to the questions that they want to answer. So moving back into just broadly thinking about remote sensing and the trends in terms of where the field is going, one of the big trends that we're seeing is the commercialization of the field. So before, this has basically been, it's a very capital intensive industry to be in. It costs a lot of money to launch satellites, and they don't always go up successfully. So you need to have even more money. This has traditionally been the realm of governmental organizations, but we've had a number of private organizations like Digital Globe, Airbus, and Deimos, which has been bought by somebody else now. These folks have been around doing this for a long time, and they're putting up their own more or less traditional sensors. And then there's a whole crop of new wave companies that are putting up CubeSats and MiniSats, which are basically like flying iPhones, right? So they've put these really small sensors into space, and they've solved some of the problems and some of the trade-offs around the not as great quality and lack of spectral depth with just putting a lot of these sensors up there, and then taking all the imagery that comes back and just harvesting what's good out of it. And then outside of that, there's a whole set of basically an ecosystem of technology companies that are out there now that are leveraging remote sensing data for specific purposes. So things like Descartes, SpaceNo, RS Metrics, Orbital Insights, and TellusLabs. Then another trend that I just want to touch on briefly is aside from the growth and commercialization, there's also work that's being done on addressing some of these trade-off issues around the trade-off between the spatial resolution and the temporal resolution. I can't see my mouse, so I can't get this thing to play. Oh, there we go. This is something pretty cool that we're working on, actually, which is basically taking Modus data, which you can see in the top right, and Landsat data, which you see in the top left, and combining it into a fused image that basically takes the positive attributes of both. And oops. Run through it. You can see that the Landsat data is super, super spotty, and this is coming from Landsat 7, which had some technical issues with the sensor. But you can see the resulting image in the bottom is pretty darn good, right? It has the spatial resolution of the Landsat, but it has the temporal resolution of the Modus imagery. And so something like this is an area of continued research for us and a lot of other people. And we think this is going to solve some of the issues around trade-offs that we have right now. So, all right, where are these data being used? And you saw some of the academic applications in Vipin's talk. And what I want to do is talk a little bit more about how these data are being used commercially. And so the big one for Telus Labs is agriculture right now. And we'll save that one for last, but I want to show you guys a couple cool pictures from some of the other players in the space. So one thing that folks are doing with really high-res spatial resolution imagery is counting shipping containers, which doesn't excite me personally, but it's pretty cool because by doing so, you can basically get an idea of the flows of goods from one country to another. You can understand volumes being imported, and it has important economic implications. Using high-res imagery to measure oil reserves, so looking at oil tanks in storage yards and at refineries. Basically, the oil in the tank has a floating lid on it because you can't just have a tank like a water tank where you've got air at the top, because that would be very, very flammable air. And so they have a floating tank or cover on the top of the tank that rises and falls. And based on the shadows cast by the sides of the tank, you can estimate how much oil is in there. And so folks are actually doing this now. Counting cars in parking lots is, again, not very exciting, but it's something that folks are using stockbrokers to understand the health of certain retailers. And then observing light emitted from the Earth at night can give you a pretty good understanding of the level of energy that's being consumed at different places on the Earth. And Vipin will recognize this one. And similarly, in an energy context, you can look at power plants or hydroelectric dams and see when they're running and approximate how much energy they're actually producing. And so here we've got two separate images. One is a Landsat on the left, and then on the right it's a really high-res image from Digital Globe. So those are all exciting areas of development, but where Telus Labs is focusing right now is on agriculture. And what we can see here is a map showing global agricultural lands colored on the spectrum from pasture land to cropland. And so the greener they are, the more intensively they're being farmed. And this is important. It's important to understand the scale of this. So 40% of the globe's land area is dedicated to farming. And so how on earth, no pun intended, can we understand the health of those crops without using something like remote sensing? I mean, there's the development of IoT sensors on farming equipment, but that doesn't help you in areas that can't buy the latest John Deere combines. So we think the answer to that is through remote sensing. And I'll sort of breeze through these because I'm running out of time. But the point is, agriculture is a huge global issue. It has a massive impact. It's using up land. We're losing forests. It consumes a lot of energy and water, disrupts nutrient cycles, it destroys biodiversity. Overall, has a massive carbon footprint, and it's growing dramatically every year. And part of the reason is people have to eat, and there's more and more people. And people are developing, people want to eat higher and higher on the food chain. It's the meat is a huge cause for a lot of that resource use, because it's it takes a lot more energy to to grow a pound of beef or chicken than it does to grow a pound of soybeans. So that being said, it's a balancing act that we're threading right now between food and the planet. And so on the left, you can see the situation where we are right now. We're not producing enough food or enough of the food that we'll need for 2050, but we're using way more of the resources than we should be. And so what we need to do is we need to bump up our food production, all the while minimizing some of our impact. And so solutions to this problem require the best available information. And so, there's enormous need for gathering better information regarding the environment and food security. So understanding what crops are being grown and where, how these are changing, and where we can improve in-season yields and things like that. These are opportunities for remote sensing to help out. And so these are some of the questions at Telus Labs that we're asking. So how will the crops do this season? How are the crops doing now? Where are they? What types? And why this matters, it's not just about food security. There's a lot of players interested right now in the types of work that we're doing. So from finance to insurance and reinsurance and agribusiness to the farmers themselves, all of them will benefit from better visibility into how the crops are doing in a given year. And so the path to going from these pictures of the planet and these pictures of crops to actionable insights is rather long and complicated. And I won't go into too much details because I've only got a couple minutes left, but suffice to say, this is something that we think a lot about. And this is just a schematic of the platform that we're building, which is essentially ingesting satellite data, on-the-ground observations, weather information, and a whole lot more, and compiling into a database of data that's available for us to draw from and build features from. And ultimately, it's the features that then feed into the models that we're building that can help drive the decisions. So I am way over time, so I'm going to skip ahead. Suffice to say, it's hard to find people who do this. This was a good one, sorry. And we're monetizing this through predicting crop yields. But that's just the beginning. Like Vipin said, there's a lot of opportunities here. The data are numerous. They're unexplored to a large extent, and they're easily accessible. And I think the challenge is for folks like us to help other people unlock the insights that are being held with them. And now's the time to do it. So with that, I'll open it up to questions.